Hello, good morning, or good afternoon, good evening, wherever you're joining in. My name is Mohammed Parvaz. I'm an assistant professor in the departments of psychiatry and neuroscience, as well as artificial intelligence and human health at the Icahn School of Medicine at Mount Sinai. And for the next half an hour or so, I'll talk to you about psychophysiological and behavioral evidence of deficits in sensitivity to reward value in substance use. First of all, I would like to thank my lab, which you can see on the left side of your screen. Our lab is motivational and affective psychopathology's lab. On the right-hand side, there are two collaborating labs. One where I did my postdoc and show some of my work from my postdoc years from Dr. Rita Goldstein. And on the right is a collaborator, Dr. Rita Kuhl from WashU St. Louis. Last but not the least, of course, our funders, the National Institute of Drug Abuse and the National Institute on Alcohol Abuse and Alcoholism. All right, so here we go. Substance use disorder. The National Institute of Drug Abuse defines substance use disorders, or SUDs, as a chronic relapsing brain disease that is characterized by compulsive drug seeking and use despite harmful consequences. What is most striking to me in this definition is the idea that it's a chronic and relapsing brain disease. So not a behavioral problem, it's a chronic relapsing brain disease, as many other health disorders are. About 40 to 75% of persons with SUD relapse within 3 weeks to 6 months period following treatment. So unlike many other health conditions, there's this really high relapse rate in substance use disorders. The other part of this definition is compulsive drug seeking and use. And this idea is that the attention bias to drug-related cues, wherever you go and you see cues that remind you of your drug use, then transitions over to the loss of control over drug-seeking behavior. And the next thing you know, you are in that bar consuming alcohol. And the last is despite harmful consequences. And that points to deficits in decision-making and in learning from adverse consequences. So even though you know that substance use or drug use leads to harmful consequences, you don't stop doing that. You keep doing that. So there are deficits in decision-making and in learning from adverse consequences. So what are some of the functional impairments in substance use disorder that we study? We study motivational dysregulation and deficits in learning and decision-making. One of the key areas in motivational dysregulation is this hyposensitivity to non-drug related reward. And by non-drug related reward, I mean money, family, like social reward. And the idea is that the repeated drug use chronically elevates the brain's reward threshold, and deficits in recruiting dopaminergic motivational circuitry by non-drug related reward. So it's not as rewarding, these other rewards compared to drug related rewards, which results to impaired sensitivity to reward magnitude. You can't compare between what's low reward versus high reward. And I'll show you some data on that. Then hypersensitivity to drug-related reward, which is drug cues trigger excessive incentive motivation to drug, really high value and high motivation to these rewards, and they normalize dopamine levels to motivate drug seeking, and that's why that's probably what transitions into compulsive drug seeking. Here we are going to concentrate on impaired sensitivity to reward magnitude, which we think is associated with deficits in reward prediction error signaling, which is a learning signal in the brain, as well as inflexible arbitration between model-based and model-free decision-making. These are two different modes of decision-making, which I'll go into a little bit more detail in a minute. Okay, so how are we looking at impaired sensitivity to reward value using computational modeling of decision-making? we look at model-free and model-based decision-making. Model-free decision-making is this automatic system that relies on habit. Um, in terms of reinforcement learning models, it's based on choosing actions that were previously rewarded. You went to a coffee shop, that coffee shop had great coffee, you'll go back there again. Last time it was rewarding, you go there again. It's computationally effective, right? You don't have to think about it too much. It's just every time I go there, I get good coffee, I'm going to go there again. But it's inflexible because even if you're not thinking, you'll just end up in that coffee shop, and therefore less accurate. But model-based decision-making is more controlled system. You plan ahead. If I go to that coffee shop that I like, would that lead? Am I going out of my way, and I'll get late to my next appointment? You plan ahead. You have a model of the world in your head, and you're planning through it. But what the issue with that is that it's computationally inefficient. You have to think too much. You have to plan too much, but it's very accurate. How do people allocate control, decision-making control based on model-free versus model-based system? So one of the theories is that it's first come, first serve. If you engage model-free control, you'll go ahead with that. If you engage model-based control first, you'll go with that. Or you can be sensitive to, or this decision could be based on the amount of reward at stake. How important is that coffee to you, right? If it's really high reward at stake, you will engage model-based control. If it's not as much, perhaps model-free control. Or the size of model-based advantage. How much are you going to get out of that decision if you engage model-based versus model-free control? And the other idea is that perhaps it's this integration of both, which is reward at stake, as well as the cost of model-based advantage that drives this decision. So are individuals with substance use less adaptive in integrating reward value and cost of model-based decision-making? That's something we'll look at using our task, which was designed by Wouter Kuhl, our collaborator, which was actually modified by Dr. Kuhl. It was originally, it was came through several iterations from Nathaniel Dost to Kathleen Hartley and others. And the idea is that you have two spaceships, either this pair or either a pair on the left or a pair on the right, which you see in the step one. And the idea is that a person has to make a decision which spaceship to take. If they take the green spaceship, and I'm looking at the left pair, it will lead to a planet that, the red planet. If they select the blue ship, it will lead to a purple planet. And one of these planets, say the red planet, is more rewarding than the purple planet. So the idea would be to try to land at red planet all the time to maximize the reward. So you see that stage one, you have a pair that you have to select a spaceship from. And step two is that you get to the planet and then you have to collect to attain the reward. And you can do that either through the left pair or the right pair of spaceships. On the right-hand side, this is how a trial looks like. So before these spaceships come up, we tell you either it's a low-stake trial, 1x, or it's a high-stakes trial, 5x, which means is your reward in the end going to be multiplied by 1, which is going to stay the same, or it will get multiplied by 5. So you pick a spaceship, you land on that planet, and let's say on that trial, the reward on that planet was 4 rewards. And then it's times 5 because it's a high reward trial, you'll end up getting 20 rewards. So the manipulation here is the reward value, either 1x or 5x. Now, how does the computation model looks like? So the model-free decision-making, where the first equation tells you it maps, it's a value function that maps a state, which is the S, with an action, which is A. And it's a typical temporal difference learning algorithm um, that takes the sigma, which is the reward prediction error, multiplies it by alpha, which is your learning signal, and updates the value function. Alpha here is learning rate. Higher alpha signifies worse reward-related learning, which means that you don't learn as much. You keep going back and forth with your decisions. On the model-based decision-making, at the first stage, the action leads to a specific second stage. You remember the two spaceships leading to two different planets with different reward values. And at the second stage, your model-free and your model-based decision-making collides because all you got to do is press a button. So what we're doing here in the model-based value computation, we take the model-free value and we times by how the staging is going to happen from stage 1 to stage 2. Right. So the idea is that model-based value computation is defined in terms of the expected values of each first stage actions using the transition structure P right here. And to connect both model-based and model-free together, we use the final equations, which is Q net, and the omega value that you see here is your model-free, model-based mixing weight. So the extent of which that you're using model-free versus model-based control in your decision-making, it ranges from 0 to 1. The closer to 0 you are, the more model-free you are. The closer to 1 you are, the more model-based you are. Okay, so what are our hypotheses here? One is the alcohol users will show less model-based, more model-free decision-making. This is based on a lot of literature that's currently there. The second hypothesis was that, which is novel to this study, is that non-users will show greater model-based decision-making during high, excuse me, versus low reward condition, as we had expected, right? Or as we talked about in the past slides. Whereas alcohol users will not show such adjustment. And the reason is that we think that there is a deficit in reward value sensitivity. So they won't be able to adjust their decision making based on high versus low reward conditions. And lastly, that alcohol users will show worse reward learning compared to non-reward. In this study, we had two groups, non-users and alcohol users. They were matched on sex, age, race, ethnicity, and education, except for the audit score, which is the alcohol use measure. And clearly, the alcohol users had high audit score compared to non-users. All right, so when we looked at the mixing weight, which was the omega value, and on the left-hand side, you have non-users. On the right, you have alcohol users. Blue bars are the low reward conditions, the green are the high reward conditions. And you can see that in alcohol users, the difference in model-based versus model-free decision-making weight, there is no difference between the high versus low conditions. However, in the non-users, there is higher model-based decision-making in high reward conditions compared to the low reward conditions. So the non-users are able to adjust their decision-making control based on reward magnitude, which alcohol users are not able to. And when we took this difference between high and low reward conditions, the mixing weight difference, we see that the higher this difference between high versus low reward condition, lower risk-taking behavior. So the less this difference is, or the more comparable high versus low conditions are in terms of your model-based versus model-free decision-making, which we see in the alcohol user group, the higher is the risk-taking behavior. And we also see that the less difference between, or the lower difference between uh, the high versus low reward condition, the more social anhedonia we see in our sample. Now, what happens to learning? Again, same thing. On the x-axis, you have non-users and users. On the y-axis, you have the learning rate alpha. And you remember that the higher values of alpha is worse learning. And clearly, there's worse learning across both conditions in alcohol users compared to non-users. And then this learning rate was associated with greater depressive symptoms. So higher the learning rate, which is worse the learning, um, higher the depressive symptoms in this sample. Okay, so basically in this part of the talk, what I did was I used this behavioral task to look at how decision making is impaired in individuals with frequent alcohol use, and we showed that they did not show sensitivity to high versus low reward conditions in their control of model-based versus model-free decision making. Now, what I want to do is that I want to show you that not only from behavior and computational modeling of behavior, we see this deficit in sensitivity to reward value, we can also look inside the brain to see whether there are correlates of brain activity that shows this deficit in reward magnitude sensitivity. So we'll switch the gears a little bit and I'll talk to you about a technique to look at brain function that we use in our lab, which is the EEG, or the electroencephalography. And what it is that it's really some electrodes that are put on the scalp. And while a person is doing an activity, there are different parts of the brain communicate with each other, or regions activate or deactivate in terms of their electrical signaling, which is picked up on the scalp with EEG. Advantages of EEG: it's a high temporal resolution. We can get data in the order of 1 millisecond, even now at sub-millisecond level. A running EEG trace looks something like this, where your x-axis is time, your y-axis is the amplitude of the signal, and each trace is an electrode on the scalp. It is clinically translatable. A lot of it's already being used in neurology clinics, especially in epilepsy and sleep. It's very cost effective compared to MRIs or PET scans. Of course, the uses are different, but it's very clinically translatable because of its low cost. It's portable, wearable. There are new headsets out there, which you can put on. They're not connected to a big amplifier that necessitates that you sit down in a lab space. You can just put these headsets on and walk around while you measure your brain activity. But there are limitations, just like for anything else. They're estimated. So when we look at where the activity is coming from, those are just estimates, excuse me, of the sources of these signals, and the signal to noise ratio is high. Okay, so this is, again, the trace, an EEG trace. On x-axis is time, and on y-axis is signal amplitude. Each trace is coming from each electrodes that are put on different parts of your scalp. What you see there also are some numbers in the bottom, and these are called event markers. So you see 10, 20, 10, 10, 30, 30. So each time an event, so let's say a picture on the screen, or a box that you have to make a decision on appears on the screen, there's a code that gets registered on the EEG trace, so that after the fact, when we go in to look at EEG data, we can tell at what instant that particular stimulus came on, so that we can look around that time to look at brain activity that is induced or elicited by that stimulus. So what we do is we look at stimulus of the same kind, so all the 10s, for example, we average them, and then we can look at one particular electrode or a few electrodes. So let's say in this case, we look at the PZ electrode, which is right towards, in the middle, but towards the back at the parietal lobe. And then when we do all this averaging, we get a wave like that, which we call the event-related potential, or the ERP. This is just a cartoon. Not the real wave does not look like this or as clean as this. But the idea is that the more, the dotted line here is your baseline. The positive peak is called a P. The negative peaks are called the N's, and the number next to them signifies the time after the onset of the stimulus that this peak comes from. So for example, P300 would be a positive peak that comes up about 300 milliseconds after the onset of a stimulus. And each of these peaks and troughs have shown to have some functional significance. What does P300 means? What does P200 means in terms of brain activity? What we know that from literature is that P300 tracks reward value. And the higher the reward value, the higher the amplitude of P300. So we are going to use this specific component of the event-related potential, or the ERP, for our second study. All right, so here we're going to look at the ERP-based detection of impaired sensitivity to reward value in substance use. This is a task that we used. I'll ask you to attend to all the way in the bottom, where I talk about the trial. For each trial, a fixation cross comes up for 1 second. And after that, one of these two fractal images come up. And these are cues or instructions. And we train the individuals before the task comes in to which of these two spectral cues are a go signal. So you have to, once you see, let's say the blue one, blue and red, you'll say, okay, this is going to be a go trial, and I'm going to have to press the button. And if it's the red and black fractal image, that's my signal to not press the button, or a no-go trial. But you don't make that decision, or you don't make that action until after this red box comes in. This is the target. And as soon as the red box comes in, you press the button if you had seen the go cue, which is the blue one, and you refrain from pressing the button if you see the red cue, which is a no-go cue. And if you get this right, you either make 0 cents, which is no money, 1 cent, low money, or 45 cents, which is a high money. And then we do this over and over and over again until we have enough trials in all 0, 1, and 45 cent conditions. And we average them just like I showed you before. And we look at one specific electrode. And what we see is a ERP like this. Again, the x-axis is time, the y-axis is amplitude. You see the P300. The solid line is the 45 cent condition, and this dotted line is the 0 cent condition. And then there's this dashed line, which is 1 cent condition, which is a little bit under the 45 line condition. And what you see in healthy controls, there are about 29 of them here. You see in healthy controls that there's this distinction between the P300 amplitude of elicited by 45 cent condition versus 0 cent condition in healthy controls. However, when we look at individuals with cocaine use disorder, this distinction between 45 cent condition and 0 cent condition P300 amplitudes disappears. It's not there. So the idea is that this wave, this component in brain activity, which is sensitive to reward value, shows that there's no difference between 45 cent condition and 0 cent condition in individuals with cocaine use disorder, but it shows this difference in non-cocaine using controls. Now we wanted to know what if this difference occurs between the high versus low money condition and doesn't happen, or we don't see it in individuals with cocaine use disorder, where in the brain might this be coming from, or might this be associated with? So we did another study where we took MRIs of these individuals, and we looked at specifically the structural MRI, where we look at brain structure, and we identified gray matter volume of the entire brain. And we correlated this difference in P300 amplitude from 45 minus 0 condition, and correlated that with the entire brain gray matter volume. And what we found is that it's most significantly correlated with regions in the medial prefrontal cortex, like ventrolateral, or in the prefrontal cortex, so including ventrolateral prefrontal cortex, the anterior cingulate cortex, the dorsolateral prefrontal cortex, and the orbitofrontal cortex. And all these regions are key regions to reward processing. So it means that this signal, which is 45 versus 0 condition signal, the higher it is, the more gray matter volume is present in the regions that are implicated in reward processing, which means that if you don't see that difference between 45 and 0 condition, P300 amplitude, then gray matter volume, or the structure of the region that are implicated in reward processing, is impaired. So not only in the first half of the talk, I showed you how behaviorally we identify the deficits in reward value in individuals with substance use. Towards the latter half, and we showed that there are brain markers that also show similar deficits in reward processing or reward value. Interesting here is that the first study was in alcohol users, and the second study is in cocaine users. So it seems like these deficits in reward value, the decision making in the behavioral study, and go and no-go responses in the second study may not be substance specific, may be addiction general. So at least between cocaine and alcohol as we see it. So to wrap up, individuals with substance use disorder show impaired sensitivity to reward value, as shown via P300 amplitude, which is a neurophysiological measure of motivated attention. We also showed through computational modeling of impaired reward-related arbitration between model-free and model-based decision-making, such that the greater impairment in reward-related arbitration was associated with higher anhedonia across all participants. And anhedonia is basically lack of enjoyment to different activities, and higher risk taking in alcohol users. Limitations of these studies, low sample sizes, especially in our behavioral study, and we are now running a follow-up study where we're going to get more people into the study and look whether these results generalize in a bigger sample. They're correlational studies, as I said, that we took P300 amplitude difference, and then we correlated that with gray matter volume. So these are not done in the same study, in the same setting, and we cannot associate causation between the two, but we're working on some of the analyses within the same study to see whether we can go a little bit closer to directional association. And lastly, in the first study, especially crude approximation of alcohol use, because we only used audit and some frequency of use measures, it was an online survey study, so we couldn't do clinical assessments to really very comprehensively examine substance use severity. Next steps would be to conduct, to do whether you do the P300 study, the MRI study, and the behavior study all within the same individual to really make these associations between these three different measures. with bigger sample size and more specific substance use measures so that we can characterize these associations more clearly. And with that, I will close. Thank you for joining us, and thank you for listening to the talk.